So Ashadul will talk about the global 21 centimeter signal in viscous dark energy models.
Good afternoon, everyone. Uh, Today I shall discuss about one of our recent work entitled Global 21 centimeter brightness temperature in viscous dark energy model. First, I would like to thank the organization for giving me this wonderful opportunity to present our work. In this work, we try to investigate the global 21 centimeter signal in the context of viscous dark energy model. Uh, The redshift of signature of 21 centimeter hydrogen absorption spectra has opened up a new window to understand the epoch of process of reionization um, and the um, factors in the early universe influencing the same. Thus, the study of 21 centimeter line in reionization era helps me understand several cosmological and astrophysical aspects regarding primordial black holes, dark matter annihilation or decay, baryon dark matter interaction, etc. According to standard cosmology, brightness temperature basically represents the intensity of of that spectra. According to standard cosmology, the brightness temperature should be minus 200 millikelvin. But according to HS light experiment, it should be much less than this limit at redshift around 17.2 or like that. So baryon dark matter interaction, primordial black hole evaporation in the form of Hawking radiation, dark matter annihilation or decay, dark matter dark energy interaction, viscous dark energy can be possible source that can modify the edges and the brightness temperature at that particular redshift range. In the present work, we mainly focused on the viscous flow of dark matter. In this case, we adopt three models from the work of Wang et al. For all these three models, the effective pressure of the dark energy is modified by is which one is, by using this term C zeta time h. Here h is the Hubble parameter and zeta is the um, bulk viscosity, which also adapted can be expressed as eta times hz. Here eta is a constant free parameter. According to model 1, we have only one free parameter, that is eta. But in model 2 and 3, we also add two other free parameters, respectively omega d and the curvature term along with eta. Oh, and incorporating this, the Hubble parameter modifies in this form. Here, first one, this one is for model 1, this one is for model 2, and last is for model 3. We can also express a general form, this one. Now, in this plot, we are showing, this is for model 1, video model 1, showing the variation of Hubble parameter with redshift z. Here, this black dashed line represents the same for the case of lambda CDM model. It is clearly seen that the variation of h with eta is not linear because it is placed in both sides of the black dashed line. It can be clearly seen from this graph. Here, in this plot, h is represented by h lambda CDM, and each lines are representing the values of h for a particular values of z. It can be seen that for each particular values of z, initially the values of h decreasing with increasing eta, but after a certain minima, it starts increasing rapidly. This black dashed line connects all those minimum points, and it can be seen that in the case of higher redshift, the minima located at higher values of eta, but at lower values of z, it tends toward 0, 1 point. and the result become more interesting in the case of model 2 and model 3. In the case of model 2, it can be seen that the variation with omega is almost negligible for the case of eta equals to 0. But when eta is raised to some certain point, for in this case eta equals to 0.5, the variation with omega can be seen. But in the case of model 3, the variation with the curvature term is not very much. Not only this viscous dark energy model not only modifies the Hubble evolution, but it also produces some kind of heat in the form of entropy due to the viscous flow of dark energy. That amount of entropy produced can be calculated from this energy entropy 4 vector, this, and the amount of heat produced per unit volume is given by this expression. This amount of entropy basically helps to heat up not only baryon temperature, but also it helps to increase the dark matter temperature. Besides this viscous flow of dark matter, we also incorporate the heating effect in the form of dark matter annihilation and decay. The rate of energy exerted in the IgM is given by these two expressions. First one for dark matter annihilation and second one for dark matter decay. Here rho chi is the dark matter density, m chi is the mass, and sigma v is the velocity average annihilation cross section for dark matter, and t chi is the dark matter and decay lifetime. We also incorporate the heating rate in the form of Hawking radiation from primordial black holes. Here the rate of energy injected in the medium is given by the upper equation. Here mbh is the mass of primordial black hole and nbh is the number density, which can be approximated using this expression. Here the important term is beta bh. Beta bh is the basically initial mass fraction of primordial black hole. Now incorporating all of this, the evolution equation for the baryon temperature, dark matter temperature, and electron fraction takes this form. Here, this dq q chi dt and dqb dt are the term which are which represents the cooling or heating effect due to baryon dark matter interaction, while this k heat is the amount of energy which helps to increase the baryon temperature due to primordial black hole evaporation, dark matter annihilation and decay. Yes, only this, and this dq dvdt and this corresponds to the dark matter viscous flow of dark matter. After all of this, we get the spin temperature and brightness temperature. Here this tau is the optical depth, can be expressed using this expression. Here A10 is the Einstein coefficient, del V is the peculiar velocity of the gas, and NHI is the number density of neutral hydrogen atom. Now here we are showing the dependence of different model parameter with the 21 centimeter temperature. This black solid line represents the evolution of T21 brightness temperature for the case of lambda CDM model. It can be seen that for the case of around 17, Z equals 17, it's around minus 200. But in the case of model 1, in absence of other heating or cooling effect, it is become slightly less than around minus 250. But still, as we know that only the cooling effect, essentially baryon dark matter interaction is the only one thing that can cool down the brightness temperature. But in this case, the evolution modification of Hubble parameter also helps to reduce the brightness temperature. And this black dotted line is the Same for model 2, where omega de considered minus 0.5. It in this case the brightness temperature decrease also. However, if we add the baryon dark matter interaction along with that, the all of these lines lie within the edges limit, that is minus 300 to minus 1000 millikelvin for redshift around z equals to 17.2. So we can say that the viscous dark energy model cannot explain the edges result alone without help of without the contribution of dark matter baryon dark matter interaction. And in this plot we introduce a new parameter to show the brightness temperature at z equals to 17.2, which is given by this parameter. Using this parameter, we try to constant the model parameters for viscous dark energy model. Here different lines represents the variation of T21 for different eta for the case of different sets of primordial black hole mass and dark matter mass. Can be seen that almost for each cases, as the values of eta increases, the brightness temperature decreases. So it supports the cooling of brightness temperature in presence of viscosity. And these are for model 2, VD model 2 and VD model 3. Here different color represents the different color represents the values, different values of T21 at z equals to 17.2, and this white region represents the region beyond the allowed limit according to edges consequence. Here can be seen that for in the case of model 2, this 3 is for model 2 and this is for model 3 for different dark matter mass. The first row for m equals to 0.6 GeV, second for 1 GeV, and third for 1.5 GeV. Can be seen that for higher values of omega de, the values of temperature is less, while in the case of model 3, the values of curvature, as the values of curvature increases, the temperature of brightness temperature increases also slightly. And finally, we try to estimate the similar allowed region in the m chi sigma 41 space. The sigma 41 is basically the parameter scattering cross section parameter between baryons and dark matter, which is given by actually the baryon dark matter interaction scattering cross section is sigma, and sigma can be expressed as sigma 0 v to the power 4, and sigma 0 also is can be expressed as its parameter is as sigma 41 into 10 to the power minus 41 centimeter square. So this colored region basically represents the allowed zone for the case of lambda CDM model, where the heating effect in the form of baryon dark matter interaction, primordial black hole evaporation are absent. So in that case, there is a maxima which is almost 3 GeV, which agrees with several recent works. However, if we incorporate the effect of viscous dark energy model along with PBH evaporation of around 10 to the power 15 gram PBH mass and initial mass fraction of 10 to the power minus 29, along with dark matter annihilation and decay, the allowed range are basically region between the lines of same color. For blue, this allowed region between this blue line and this blue line are shifted toward higher values of sigma 41. This work is recently published in Journal of Cosmology and Astrophysics, where the details calculation are available. It is also available in our archive preprint. Thank you very much.
So what? Maybe you said this and I didn't understand, but exactly what caused your 21 centimeter signal to go below the lambda CDM value?
Lambda CDM actually
Is
it,
that a
it, it requires additional cooling effect of baryons that can be achieved using from the baryon dark matter interaction. Actually, in that case, we considered cold type dark matter. So due to interaction between baryons and dark matter, the temperature of baryon increases. At the same time, the temperature of dark matter increases, and at the same time, the temperature of the baryon decreases.
Yes, can we have a viscous dark energy model, which does not have spatial fluctuations?
Uh, Maybe, but I don't know whether it is possible to have fluctuation.
any more questions, comments? Karan?
So I saw that your Hubble parameters, Hubble function as a function of red shift is deviating from the lambda CDM, right?
This one.
The ratio is less than 1. Yeah, so if you go even further, let's say 1000, and so the ratio is around 100 or even more than that. So will not that affect other observations like CMB observations?
Like same development. Yes, it should be, because it should be, but we did not check that. We actually only checked for this.
Yeah. Now, for example, how structures are formed in this kind of models, and there are constants already constants on that, whether they are consistent.
Actually, there is a constant in the paper of most probably Wang et al. They used they actually compared with CMB data most probably, and the values of eta was maximum values was most probably 0.8 or like that, but I cannot remember actually the exact value.
Okay. Yeah. Thank you.